Hello, today we're going to be talking about projectile motion from topic A.1.4 from Kognity. I love projectile motion. I love throwing things out of buildings. So, projectile motion, defined on the Wikipedia page, is a form of motion experienced by an object or particle, a projectile, that is projected in a gravitational field, such as from Earth's surface, and moves along a curved path, a trajectory, under the action of gravity only. So, trajectory is the path followed by a projectile launched at an angle. So, assuming you guys have done the Kognity already, hopefully, I would really hope so, you guys are probably familiar with linear motion. You also did this last year, if you were here for that. Actually, all of you were. So when you have linear motion, you have something just moving in one dimension. Boo. No one likes that. In projectile motion, you're going to be moving in 2D. Which means you can do cool things like this, where you like curve and you're not just a dot. And we're not going to be talking about, we don't have to talk about in the physics curriculum, would be 3D motion, which is really hard because this iPad is actually in 2D. So I have to get like, something like that. Good thing is we don't have to do that. We have to do this. If I can draw a circle. All right, let's get rid of that. No one likes that. So, and also I have my notes printed off on the side here. You can't see, but I'm using for reference. So it's gonna be a little loud in the background. So let's take a little detour to Newton's second law. So this law, as you're probably familiar with it, just says that force is equal to mass times acceleration. And we also know that an object in motion stays in motion. However, there's a common misconception that when an object is staying in motion, that means that there has to be continued force so that it has velocity, but that's not true. You can see from this equation here that force is directly proportional to acceleration. So in order for an object will stay in motion as long as there's no force that's going to stop it, but an object doesn't need continued acceleration to keep moving, so there doesn't have to be continued acceleration moving on the object. So if we had like a hypothetical here, we love hypotheticals here, we'd say we have no gravity, right? We've got this projectile, we're throwing it, oh, that's an eraser. We have a projectile, we're moving it this way, and it's just gonna keep going and then stop, right? It's no gravity. Let's pretend there's like a cannon here. If we had the same object, oh, they're gonna spell check me, aren't they? Oh, I hate it here. So if we had the same object in with gravity, right? This is gonna be point like, let's pick a weird one. Make this point mu, because I can do that. It's my video. This is point mu, right? Same point, and you're just gonna see that the up and down is what is affected by gravity. So this shows us that the components of velocity here, if this is velocity, the components of velocity show that Vx here, when you gravity only impacts the vertical velocity, so going up and down. However, the horizontal velocity vector here is not impacted by gravity. It stays the same because it still has the same range. You guys know what I'm trying to draw. same range. So, knowing that, and knowing that my slides are so not in order, there we go. Okay, one more thing that I want to talk about why I'm here is that the trajectory of an object, let's go back up, that's going to be parabolic. You guys know what that is, right? So it's going to look something like this with an axis of symmetry. And so when you have, it's going to be parabolic as long as there's no air. You guys know what I'm talking about. No air resistance. So let's say we have an example here. Let's say we've got a nice building, got some windows, probably have more windows in real life, and then we have some sort of object, right? And we're going to throw, I don't know what object we're going to throw. We'll throw some sort of a spear. Probably cow, maybe not a cow, I don't know. But we're not actually throwing it. We're just dropping it off of this point right here. So we have this point here. And let's just mark a couple points here. So if you look at these points, you can see that there is going to be I'm going to do it in yellow. So each of these points has something like this, and that's going to be Vy, that's going to be Vx, Y, X. You guys know the drill. So the Vx is going to be horizontal, and Vy is going to be vertical velocity. What we've already said is since this object is being dropped and there's no air resistance, that means that there's only going to be for the vertical velocity, that's going to be impacted by gravity. So, well, gravity and time specifically. So if you're actually looking down here, that's going to be gravity times time, etc., etc. And then the horizontal velocity is going to be the same. So if we have, I'll make a clearer example. So we've got something like this, some sort of cliff. I don't know, can't draw this. And we have a cannon. And it's going to be, this one's actually going to be shooting something out. So it's going to look something like this. It's going to get here, and this is the cannonball, all the same color. Then you'll have stuff like this. I'll draw less of them. This is gravity times times, where we're defining gravity is 9.8 meters per second squared. To the negative second squared, because we're in IB now. So let's say that this cannon is, and it's making a 90-degree angle right here. So we can just we don't have to talk about the angle yet. So let's say that this is going at 20 per second, and I just took a chunk out of it. So 20 meters per second, and then this is going to be its Vx, and that's going to stay the same. Ignore the red box. And it's going to stay the same even as it hits the ground. That's horizontal. And then for vertical, let's draw this one down then. It's going to be gravity times time. So there's 1 second elapsed times 9.8. That's going to give you 9.8. So that's going to be the horizontal velocity. And then you would have the same thing here if this was like 2 seconds. Or let's say it's 3. It looks more like 3. So you'd have 9.8 times 3. And that would be 29.4 meters per second. Down. And just a reminder that the horizontal velocity is all the same because there is no air resistance. So, like I said, on this diagram, we have 90-degree angle, right? But life's never that simple. Why would it be that simple? That would just be too easy. What if we added an angle? So, oh, this is fun. My diagram that I printed off is actually cut in half. So, same cannon, he's on a cliff, a little thinner this time, and he is at an angle, so it's going to be showing, again, we're going to separate this into the components. We're going to have the vertical velocity and the horizontal velocity. I'm going to learn the difference between the two of those when I say it at some point. So, how do we, find that? What do we do? I have a solution for you. It's trig. That's always the answer, by the way. It's always, the answer is always trig. So, let's say that we want to find the vertical velocity right here, right? So, if we remember that cosine of an angle, it's called theta. Actually, hold on. I'm going to add a little bit to my diagram here. We're going to call this thing, I'm going to call it A. If we remember, cosine is equal to adjacent for hypotenuse. I really hope you guys know this. Then we can show that this Vx, right? This is a rectangle, by the way. This Vx is going to be, if we're trying to find theta, we're going to be going adjacent, which is Vx over A. So that means that, actually, no, it's going to be cosine theta equals Vx over A. We solve that for Vx, and then you get A times cosine theta is equal to your horizontal velocity. Do the same thing, or slightly different, for vertical velocity. Then you remember that sine, what we're going to use here, is equal to opposite over hypotenuse. So if we have sine theta is equal to, and this one's going to be opposite, so this opposite right here is going to be also equal to Vy, and you just move it over, and then that over the hypotenuse, which is again A, so you have for A, solve it, then vertical velocity is equal to A times sine theta. Yippee! So now we have this, and if you want to, let's do a little bit of a worked example. Let's say cannon again. My cannons are getting worse every time. Let's say it's 60, and you're given an angle, it's about 40 degrees, and this is meters per second. Trust me. So the vertical velocity is going to be equal to 60 times cosine 40, and that's horizontal, and then vertical velocity, I can't draw Y's, it's going to be 60 times sine 40. Put that into your calculators, and you're going to get Vx is equal to 38.6 meters per second, and then Vy equals 45.9 meters per second. Meters per second, not whatever that W was. So, now you know what the components are, and you can use those components like we were doing earlier to find out the velocities at the different points, which we're going to do an example of. So let's do another graph. I gotta make sure this one actually looks good, because I'm gonna try and do something with it. So we have our starting point here, and let's say that our change color. Actually, change color. There we go. This is going to be equal to 23, right? Close enough. Technically, it's 22.98, but 23 here. And so our components are going to be 19.6 and 12, which you can, if they also, by the way, if they only give you the components, you can use hypotenuse is equal to a squared plus b squared, or, nope, don't solve that for me, or if we're using the early example, you can use a squared is equal to, which we're defining a is that thing right there, is equal to ex squared plus by squared. And, okay, getting back to this example, so let's say we've got a couple points, something roughly equal, something there, yeah, sure, close enough, and then something down here. So the components of these parts are going to be that, then if you have time, so you find these are all going to be 12, no matter where they come from, because there's no air resistance. And then the vertical ones are going to be, I wrote this yellow on white, I don't know why I did that. The first one, 9.8, because this is t equals 1, and then this one's going to be t equals 2, that's not a 2, so that means that the second one is going to be 19, oh, wait, hold on. No, okay. Forgot to draw a point here. I forgot the part where we're going to do, this is equal to 12, and then this one is going to be 0, because this is going to be the top, where we change from 9.8 to negative 9.8, and then this first one is going to be 19.6, negative velocity, because it changes after you go from 0, like this. So you're going this way. And then down here, I think I calculated out as whatever the value is. It would be something, it would be like 29.4 if it was like t equals 3 or something like that. So, and this works because this is a parabola. Yeah, that's an axis of symmetry. Sure. This is a parabola, so it's going to be equal on both sides, because there is no air resistance. I love saying that. I hope I can say that forever. That's that. I just went backwards. Okay, I'm done. So, well, not done with the video. So, how do you calculate the components? Actually, we already did that. So, we have all of this, right, of velocity, right? From Kognity, there's something they call the three questions. Technically, Kognity says there's 4 of them, but they included something else in there that we're going to talk about a little bit later. Oh, this is really choppy. Okay. So, one of the questions IB or AP is going to be asking is how high, or they're going to be asking jump, and you're going to say how high, but actually, no, they're going to be saying how high does it reach, which essentially you're just going to be looking for the vertex. So, I'm going to remind myself not to print this next time. Another graph, maybe one that's level. Sure. It's the vertex, is going to be constant, and this is going to be 0. So if we were to do this without numbers, then you would have, we can use this equation from the formula sheet, and something that you've probably encountered, but I'm just going to remind everyone, is that when you have u, which I'm going to draw like this because, see, there's like no difference between my v's and my u's, so my u's are going to have those, and that is going to be equal to this, or initial velocity. And then also they have s, which is equal to x, or displacement. Yeah, iOS 18 added a feature where they try to spell check my notes, which is really funny. So we're using the equation that I'm going to move down. Definitely not flexing. So we have this is equal to u squared plus 2as, where we're going to define u is equal to initial. So this is going to be initial, and we're only going to be looking at the, we're only going to be looking at the vertical. So we're actually looking at y. You want a y here, and a y, and everyone gets a y. This is equal to the initial times sine theta, right? Because we remember that from above. I'm not going to scroll to find it. You can find it. And then we have everything else that probably going to give to you, or you're going to be solving. So you would start with this equation here, and you can transfer that to find s, which is going to be your displacement, which is what you want because you're trying to find how high it is. And you're going to end up with v squared minus u, actual u, and then 2, just the 2 from there, times acceleration, which is going to be gravity here. So let's say we've got an example, tiny mini example. And that the velocity that they give you is equal to 20 meters per second. Then the initial is equal to 20 times sine 60. And then the velocity y is going to be equal to 0 when we plug it in here. So the s is going to be equal to, that's going to be a 0, by the way. So we end up with s is equal to 0 squared minus 20 sine 60 squared. You can use your unit circle for this. And then 2 times, and remember that we're going to be looking at gravity, and gravity is going to be going down here, or pulling the spherical object, which might be a cow, down. So it's going to be negative 9.8. Then plug this into your calculator, or don't actually, I can do it for you. That's going to be equal to 15.3 meters. Fun times. This was 1. Number 2. I can feel my iPad. It's so warm right now. How long was, I'll just put was here, was projectile in the air. This is also going to be known as the time of flight. And notice how this first one, how high, is going to be in the vertical plane. No one go through this video and correct my spelling. I think I messed up a bunch of words. This one also is going to be in the the vertical plane. I can see the time on this video, that's why I'm speeding through it. So for this one, guess what? Another graph, something here, and then in this example here, actually, no, I'll do the example in a second. This is going to be time, right? So we're looking for how long it's in the air, so just gonna add this here and I'll explain this in a second. So for this one, we're going to be using from the formula sheet, one you should be familiar with, plus acceleration times time. Solving it for time, we get this, or this is actually g, which is, actually I'm not going to define that, you guys know what it is. So our initial here for y is going to be equal to u times sine theta again, where this is u, this is the normal u, and then the vertical component, the initial speed. And yeah, this is cropped really badly for me on my notes. So, like I said here, that the this is going to be equal to negative v, because when the ball comes back down the same speed up and down, because there is no air resistance, and it's a parabola. So that's why. It's just a sign change. With the same magnitude. So, quick little example. Same one. 20 meters per second, and then angle of 60. Plug it in where t is equal to negative 20 sine 60 minus 20 sine 60 over 9.8. Negative 9.8, gravity is going down, times equal to 3.535, which is equal to t equals 3.5 seconds. Did I circle my other one? Okay. Number 3. We're so close to 30 minutes. And yet not done. So how far away horizontally does the ball land? So this is going to be asking for the range. And now we're going to use the horizontal plane. Finally. So this is also cropped really weird. Okay, so one more time. Now this, and we're gonna have the equation. So this is also from the formula sheet that you have, just u plus v times t over 2, just as kind of like almost like an average, where we can find the components. And since there is no air resistance, the velocity is going to be equal to initial velocity for x, no air resistance, and yeah, okay, I just wrote the same thing twice in my notes. So we have this one is actually going to be helpful if you have the time from the second question. So it might be helpful to solve for the time because you're going to be using that in this example. Say we use the same things. We're going to be using what are my constants? 60 degrees. So we have S equals U plus V time for 2. And then if we're looking for the range, we can set, we have the acceleration is equal to 0. And we're actually not using it in the equation because we're not using it because it's when it hits the ground. So S equals the time, which is 3.5. I'm just moving it up over here. 20 cosine 60 plus 20 cosine 60 for 2. Let's see what I think it's 25. Probably. Yeah, I think it's 25. Yippee! Alright. So, looks like we're probably done or something, I don't know. No, hold on. Wrong lesson. Sorry about that. Got distracted by the Swan Lake. Got distracted by the Tchaikovsky. So, I've been saying no to this a lot, but you know what we are going to be doing right now? Air resist. Just kidding. He's happy. He loves Newtonian physics. He believes in Newtonian physics. So, this is new content. We technically didn't do this in AP Physics. Yeah, we did not do this. So, air resistance sometimes is going to be called, maybe sometimes it's going to be written, fluid resistance. That's because air is a fluid. So, another helpful diagram. Say we have this, right? And let's look at what we've been normally looking at. If we start from the ground, we can have something like this. And that's going to be, FA. Which is what I'm going to be calling air resistance from now on, FA. So if we had air resistance, let's put it red, then it would start from the same point, go, and then stop. So that's going to be FA. And then let's draw. These are the vertexes and points. Vertex and point. Okay, actually, I'm going to be really consistent, so I'm going to slightly redraw this. It's going to make sense in a second. Why? Because you can see that this segment right here is shorter than this segment. However, this segment is longer than this segment. Trust. So, we can make some assumptions when you have air resistance. And so that's going to be that the trajectory is a different shape as without air resistance is parabolic. Second one is that the max height is lower, impacting the vertical component, and that the range is shorter. You can see that all here. You have the trajectory is a different shape. This is not parabolic. This should be parabolic. Pretend it is. Pretend this part is parabolic. Max height is lower, and then range is shorter. Two-hand. It's not letting me move down. Okay, there it is. It's letting me move down. So we can say that because of this, we can make some, what did I call it? Yeah, sure, okay. Not assumptions, but these are deductions we can make. So the velocity is going to be lower because air resistance decreases acceleration. This ties back into the acceleration I was talking about earlier, where you can still have an object, even if there's no acceleration moving on it. It's going to continue moving until something stops it. Typically, when you have projectile motion, air resistance is going to be what's stopping it. So if it's not accelerating faster than the air resistance can stop it, then the object is going to stop moving. That'd be really scary. Imagine you're skydiving, you just like sit there in air, you're like floating. Maybe that would be fun. Second one is the range, which is lower, like we just said. Oh wait, actually that's not range. It's the projectile is going to reach the lower, but it's going to be the max height. It's faster. And this is because lower time flight upwards, because air resistance is going to be pushing on the object as it's being thrown upwards, and it's going to stop it because it's going to be air resistance plus gravity, and that's going to stop it. That's going to make it slower. And then the object is going to be, so the object is going to be experiencing FA. So after it reaches the vertex, it will have a lower range. But it will reach the lowest part here. It'll reach that faster. Sorry, no, it'll reach it slower. As air resistance upwards will slow its fall. So the time of falling will be longer. Now for the example problems with equations. Just kidding. We only have to know the qualitative of what happens when you have air resistance. So we don't actually have to know any like formulas going on about air resistance, from what I've heard from Kognity, which is really nice. All right, and that about sums it up. I was gonna do summary, but no, I don't think we're gonna have time for that. All right, thank you for watching.